Okay, so this is lecture 16, first part, and today we're going to talk about how to compute treewidth. So I give you a graph G, and G is a graph, and we would like to compute the treewidth of G. Okay. Now, of course, we don't really want only to compute the treewidth, we also would like to compute the decomposition, right? Unfortunately, this problem is NP hard. NP hard, and it seems, in fact, pretty difficult to do. So, since we're in a fixed parameter tractable course, the question is, can you do FPT? And the answer, of course, is yes, right? Why is the answer yes? Well, if the treewidth of G is K, right, then we can look on the family of all such graphs. Think about G hat K. All graphs that have treewidth at most K, and this is a minor closed family. All graphs with TW smaller than K. So this family is minor closed. Okay, and Seymour and Robertson theorem, or Robertson and Seymour, tells us that minor closed family can be recognized, in polynomial time, right? There is a finite list of forbidden graphs, such that if any of the forbidden graph appear in the family, then it's not minor free, right? So Robertson and Seymour. Right? The problem with Robertson and Seymour, of course, is that it's an existential theorem, right? And having an existential theorem is not very useful, right? It doesn't mean that we really know the algorithm. In particular, this forbidden list of graph first, it's probably monstrously large. It's constant but monstrously large. But secondly, we don't even know what it is and how to compute it efficiently. So that's a dead end. So we need to really come up with a real algorithm, not just an existential algorithm. And at that point, we don't know how to do it exactly. So we are going to do some approximation. Well, the running time would be FPT in the treewidth K. Okay. So there are several results known. I should say that maybe the best result, as far as I could find, although it's mentioned only in the notes, is K log K, K log K treewidth in polynomial time, polytime, in K and N, right? So what do I mean by that? You give me a graph that has treewidth K, and there is an algorithm that would output a tree decomposition of width K log K. So it's a log K approximation. It might be square root log K, it doesn't really matter. And this algorithm is pretty complicated. It essentially uses sparse cut and stuff like that. It essentially follows closely the stuff we're going to do in today's lecture, but it's way more complicated. But the nice thing about this result, this is strongly polynomial. I'm pretty sure it's square root, by the way. It's strongly polynomial in both K and N. We are not going to be able to do quite as well. Okay, so currently the best results known, according to the book, is an algorithm that in that time compute treewidth k, if it exists. Treewidth the composition of width of size k, if it exists for a graph. So the running time is of course quite bad. So the game is of course going to be how to improve the dependency on this parameter k in the running time. We would like it to be, as good as we can get it. What we're going to show is a somewhat faster algorithm that provides an approximation. Right? So the running time is this, a to the k essentially, the dependency on k, but unfortunately the treewidth is 4k plus 4 instead of k. So you have to trade off between running time and quality of approximation, and this algorithm is going to be based on the idea of separators in trees. So we're going to next speak about separators and what to do with them. Okay, so in our case, first we need to remember what is a separator. And let's start from the tree case. Tree, right? So I have a tree, and in fact it's a binary tree. Right. So I have a tree, it's a binary tree. We can assume there are weights on the vertices, because that would turn out to be useful. Not all the nodes need to be binary nodes, right? And then some of the nodes might have weight 0, some of them might have weight 1, some of them would have, whatever weight we want. And the first observation is that there is always a vertex in a tree such that if we remove it, then, we delete this vertex, right? Then there are several connected components remaining. This one, and of course the remaining three outside, right? So 3 components. So let's call them T1, T2, T3. If it's a binary tree, it's going to be at most 3. It might be 2 or 1 in fact, but that's not an interesting case. So the weight of each one of those trees, and in fact it would be convenient, so one has to be a bit careful about whether or not we include the separator, So let's assume that we don't include the separator, just conceptually for the time being. So the weight of each one of those trees is going to be at most half the weight of the original tree. So this is the claim, that there is always a separator node that has this property, where weight is again the weight of the vertices. And the proof is easy. You just, you kind of ask yourself, is the root good? If I take you root the tree, of course. Well, that was my assumption from the beginning, but you start from the root and you say, is it good? If I remove it, do I get the property that every one of the subtrees weight at most half? If it is, we are done. Otherwise, there must be a child which is heavy, right? So you continue down to this child, right? And you continue the argument, right? So essentially what you do, you're going to follow the heavy path in the tree, always going into the subtree that have weight, at least half the weight of the tree, until you get to a node such that the weight of its subtree is larger than half the weight of the tree, strictly larger than half the weight of the tree, right? But the weight of its 2 children, right, each one of them has weight smaller than 3. Sorry, each one of them has weight smaller than half. right? But at that point we are done, right? Because this means that if we remove this node, then each one of the two children would be weight smaller than half, and of course the tree above this separator is also going to have weight at most half. So we are done. So and this of course can be computed in linear time. So this is the separator. The thing is that usually we are not interested in, this breaks the tree into 3 trees, but usually for algorithm we want to break the tree into 2 pieces, right? So we can take this tree, break it into 3 pieces, and then put together 2 of the lighter pieces together so that we continue working on those pieces. And if you do that, then you get a slightly weaker result. You get that, let's call it lemma, given a tree. By the way, I should say that the above result with half was true for any tree. We never used the fact that it's a binary tree. Okay, given a tree, right, a binary tree. Here it's going to be important that it's a binary tree. I think it's important. Let's see. Given a, well, in our case we need a binary tree. Whether or not it matters, we can figure out later. Given a binary tree, there exists a vertex, there exists a vertex, and 2 trees, and 2 trees. Trees, right, T1, T2, and the vertex S. And the separator vertex X. Such that, so T1 and T2 the weight of Ti is smaller than 2/3 the weight of the tree, and right, and T1, T2 plus S, cover the tree, equal to T, right? Which means that, S is the only interaction between those 2 trees. T1 and T2 are not really trees, they are forests in this case, right? So the promise reduces from half to 2/3, and the proof is the same proof, right? You go down, you start in the root, you go down to the child. If there is a child of weight 2/3, then when there is a node of, if you have a node of weight 2/3 and all its children are weight larger than 2/3, you stop there, right? And you remove this node and so on. And this is it, right? Now we need to separate S from the T1 and T2, and then you just apply the argument we just seen above. It just follows immediately. Now it's easy to see that this is tight. Just consider this case, right? So every piece, maybe we should make it a bit longer to make it clearer. Well, right, so think about every one of the leaf being weight 1 and the node in the middle having 0. So clearly the only option for separator is the middle node, right? But then one of the 3 would be 2 of the leaf, so it would have weight 1, and the other 3 would have weight 1. So it's 2/3. And we needed to put S apart because, formally speaking, S might be all the weight in the tree, right? It might be that all the nodes in the tree have weight 0, and then there is one node that have, all the weight, and then if you put in a separator, it breaks the tree, right? So you need to kind of include us into that. Okay, so this is all very well known. It essentially says that there is a one node separator for tree, either half or 2/3, depending whether you want to break it into two groups or you're allowing more sub problems. And this is clearly can be used for treewidth, right? Because so imagine the following situation, and this is kind of the key thing going on, right? We have a graph. I give you a graph, and I tell you that its treewidth is k, right? And there's going to be some active vertices. What do I mean by active vertices? We will need to wait and see a bit. Okay, but think about them. Essentially, think about them as the interface vertices of this piece of the graph to the rest of the graph, right? We are somewhere deep in the recursion. There is a huge graph, but we have a piece of the graph, and we have all the vertices that somehow communicate, have edges to the outside of the graph, right? And we have, so let's call this piece W, right? We are speaking about the induced graph on W. Okay, and now we know that this piece of a graph, this subgraph, it has a tree representation, right? A treewidth representation of width k. To remind you, treewidth is a hereditary property. So if we take a subgraph, it still have treewidth representation of width at most k. So there is a treewidth representation. In fact, we can assume it's a nice treewidth representation, and then we can apply the above. Again. Right, so, we are going to put the weight, so a node here might appear in several nodes, right? There might be a subtree corresponding to it. So, we can do various things, it doesn't really matter. We can, for example, for example, we can put all the weight of a vertex in the highest node that it appears in, right? This is this forget node, if you remember this nice representation thing. So we can put all its weight of 1 here, right, of this node, right? So this node would get the weight of the total number of vertices that are introduced in this subtree, or forgotten in that subtree, right? There's this confusing thing. Okay, so now we can find a vertex, so the important thing is that here we put the weight only for the active nodes, only active nodes. Right. So we're going to find a separator in this tree, in the tree decomposition tree. This is a separator, right? And the separator tells us that, well, the separator node corresponds to k nodes, right? It's k nodes because that's the size of the bag. Size of bag. Okay. So if we remove the bag, right, then we break the tree into pieces, and each one of them is relatively small. Each one of them is going to be 2/3, right? So if the weight, let alpha be the total number of active nodes, right? So each piece, we're going to break it into 2 pieces. Each piece, total weight, well, the total weight is going to be 2/3 of alpha, right? And what we're going to do here, which is very important, is that we're in fact going to send the separator node with the 2 pieces, right? So we are in fact, keeping the separator bag in those 2 pieces. So it's going to be plus the separator nodes, right? And in fact, the separator nodes, the are going to be added. So the number of active nodes in the sub-problem is going to be bigger. So maybe I should draw it, right? Think about it like that. There is the separator node. What we're going, and then again, this is the tree decomposition. So this is this, every vertex represents a bag and so on. And what we are going to do, one subtree subgraph of the problem we're going to generate is this, and the other one is going to be this. And the important thing is that the bag, the separator bag is being shared, right? So this breaks our graph GW, the current graph, into two pieces, right? And the important thing is that every one of those pieces is going to have 2/3 alpha plus k active nodes, and to make the thing work, we need this to be smaller than alpha, right? Because that says that the number of nodes is not increasing. So if you reorganize this, you will get k is smaller than alpha over 3, which means that this would work with alpha larger than 3k. So let's take alpha to be, I think the book takes it to be 3k plus 4. Okay, so what does this mean? This is kind of important to understand. So here's what it means. It means that if I give you and conceptually don't think about it as 3k plus 4. It's much better to think about it as, let's say 6k, right? So a slightly bigger number. So I give you a piece of a graph that have bounded treewidth, right? And it has those active nodes, these interface nodes, right? So what I just proved is that there is, and the number of this interface node, let's say, is 6k. Exactly 6k, right? So what we just proved is that there is a set of k nodes such that we can now break the graph into two pieces. This piece and this piece, let me use a different color. And this piece, such that the two pieces share only k vertices, and the two pieces are smaller. Right? I'm not saying anything about how imbalanced they are, right? It might be that one piece is, very small compared to the other, but we don't care because we are building a treewidth, right? So, and in particular, we know what the interface vertices are. Those are the, the active nodes. So now we are done, right? Because if we can compute the separator nodes, then we are in great shape. Why are we in great shape? Well, let's take all the active nodes right, plus we add to it plus the separator bag nodes, right? So we create a bag for that, and then we just recurse on the, let's call it H and J, right? And then we just recurse on H and J, the two pieces, where in the two pieces we take, let's look on H. In H you take the bag nodes as active, and also of course all the active nodes that are inside it. But the above analysis, this inequality says that the number of active nodes in fact decreases if we take it to be strictly larger than 3k, right? Like 3k plus 4, right? It might decrease by 1, but it doesn't matter. It at least decreases, right? So this gives us immediately a way to compute. If we can compute this separator bag that always exists, that's what we know, then we can compute a tree decomposition, right? So far, so good. The important thing is here to observe is that when we declare a node to be active, this is going, when we send the graph to the child to build the 3D composition, the node is marked as active. Nodes cannot be marked as inactive, right? So, you know, so everything is valid. There's never going to be an edges between pieces that, you know, between nodes that are not in the same bag. So this is indeed a valid 3D composition, and you know, we are going to get a 3 or 4 approximation, as long as we can find those active pieces, right? So this is part 1 of the algorithm, right? If there is a node, so what did we show? We showed that we essentially showed an algorithm for computing treewidth decomposition if can compute separator. Okay, so now we are down to this problem, right? I give you a graph. I tell you it's a treewidth K. I give you some active nodes, right? Let's say like that, and I want you to find the separating, you know, the smallest vertex separator. I would like to find the smallest vertex separator, right? Now, the problem is kind of very clear, right? That why it's not going to be easy, because to begin with, we need to guess which vertices are on one side of the separator and which vertices on the other side, right? So in our case, we don't care too much, right? Because we can just enumerate all possible guesses, right? So let's assume that we do that, right? We have to do that, and in fact, this is going to be the bottleneck in all the algorithms, which is how do you find the separation? This approximation algorithm that I told you about earlier, that is strongly polynomial both in K and N, in fact has, you know, uses you know, lifting and semi-definite programming and projection on a line and ARV to find an ordering of the vertices such that it has a polynomial number of such assignment that it tries. That's really what's going on, and that's why they get the good approximation. So, you know, this part is complicated. In our case, we are just willing to try all possibilities. Okay, so we tried all possibilities. So now we are into this following sub-problem, right? I give you a graph. There are two groups of vertices, left and right, right? And I would like to find, this is two subgroups. They don't cover all the vertices. There are a lot of other vertices in the graph, of course. And I would like to find a small separator. I would like to find a small group of vertices that break the graph into two pieces that separate the left part from the right part, right? So fortunately, we can do that. This is easily computable. This is just network flow. So you have to be a bit careful because this is network flow. So first, the graph is undirected. So you replace every edge by, you know, two edges, right? So you make it directed. And then the other problem is that here we are interested in vertex separator, not edge separation. So all the edges that we created here, we put infinite capacity on them, right? And every vertex now have edges coming into it and edges coming out of it. And what we do, we rewrite it, right? We create this new, an incoming vertex, an outgoing vertex, right? And we create an edge that come across, and this edge is capacity 1, right? And now we do the regular, you know, so now we modified the graph, and all the vertices on the left, we connect them to a source vertex, right? again with infinite capacity, and all the vertices in the array connect to a sink vertex, again with infinite capacity on the edges. And now we compute the maximum flow on this graph, right? Max flow, right? And of course, there is this famous mean cut max flow theorem, right? The mean cut max flow, mean cut max flow. Mean cut max flow says that the maximum flow in the network we just computed corresponds to the minimum number of edges that needs to cut the graph, disconnect the left side from the right side. But in our case, you cannot take any of the edges that infinite capacity, so you're going to take only the edges correspond to vertices. So this gives you the set of vertices you need to remove from the graph to disconnect the left from the right, right? And you know, so we need the fact that if G has treewidth K, then the number of edges in the graph is at most of Kn, right? And the maximum flow we're going to have is K. So running maximum flow on such a graph takes K squared n time. Computing max flow. Because you have to do K augmenting path. Computing max flow in this case. And now we are done, right? Because why are we done? Well, because now we are essentially done, because the running time is going to be 2 to the alpha, right? K square, you know, the size of the graph, the number of vertices in the piece that we have, right? So we compute this is the time it takes us to compute the root bag, the root. And then we root bag in the tree decomposition, And then we continue recursively, right? Once we have this separator node, we know the pieces and we continue recursively. So this all is going to work. Alpha is something like 3k plus 4. And if you think about it, you know, since we don't care about running time, the polynomial running times, this says for graph G, overall the graph G, it would take us to, you know, G graph with n vertices, and treewidth K. So for a graph like that, it's going to take us, you know, so we're going to pay 2 to the 3k plus 4 times k squared, I think, times, and this is to the time it takes us to compute the root, but then we have to recurse, right? And, you know, the size of the tree is going to be n, so we have to do it n times. So we're going to get running time like that, which is essentially what we promised, okay? And you know, the factor n squared can be improved, but we don't care about that here. Okay, so that's the algorithm. The only thing I didn't tell you we need to prove is this claim that indeed the number of edges, if G is of treewidth of G is K, then the number of edges of the graph is small. The number of edges of G is smaller than Kn. And the proof is not hard. You need to think about it for a bit. The book leaves it as an exercise, but let me just tell you the proof. Just look on the tree decomposition, right? And root this tree decomposition. We can always do that. every node now corresponds to a tree, right? And for every tree, just take the lowest, you know, the closest node to the root, right? That would be the marker of this vertex, as we did before when we talked about the weight, right? So when we do that, right? When we do that, the key observation is that in this tree, consider the node with a marker that is furthest away from the root. Right? So there might be a node very low. Right? This is the lowest marker from the tree. Let's call it, in that sense, it's marked vertex U. So the key observation is that U in the graph, since it's no other vertex is introduced here, U can be connected only to the node in its bag. Right? There are at most such nodes, which means that U, the degree of U in the graph, is K. Right? So now you remove remove U from the graph, and you repeat this argument. Right? And that immediately implies that the number of edges in G is at most Kn, which is what we needed. Okay. So we got that we can compute the tree decomposition in approximately up to a factor of 3 in FPT time.